Hello, it's me again. You miss me yet? Today we're going to finish up the diode lab, the lab for which our target is to measure Planck's constant. We like this lab a lot because it's a modern physics lab, and you get to Planck's constant is basically a important quantum mechanical constant, and it's a quantum mechanical phenomena that takes place inside the solid state of the diode that allows us to determine Planck's constant. The thing is, all you have to do is measure the activation voltage for each diode, and that's not necessarily trivial because you have to have some methodological thoughts to figure out how you want to take that IV graph and decide when exactly it is you're going to say that the current started flowing. But you'll figure that out and describe it, and then you have your voltages and you can quickly get Planck's constant. And we just thought that while the lab is interesting, it's a little bit too short on activity. And if you think about it, the other thing that's important in this lab is the wavelength of the lights. And being experimentalists, we thought we really ought to try to measure everything and not just rely on the wavelengths that were given. So that's what the rest of this lab is about. You might decide after seeing this that the wavelengths that we get are too unreliable, and you may go ahead and do the Planck's constant analysis using the given wavelengths. But I do want you to include a sheet in your report where you take the current data that I'm about to share with you and use them to determine the wavelengths of light. We're going to use a grading spectrometer, and the theoretical formula is n lambda equals d sine theta, where we want to figure out lambda. We're only going to look at the first order, so n is 1. D is set by the grading, and so really if we measure theta, the angle that the diode light bends through the prism, we should be able to figure out what the wavelength is. So with that, let me show you the equipment and explain how this is done. Okay, so here is our kind of lollipop that's got all the diodes on it, and it's pretty much set up like it was last week. Here is the DC power supply that's controllable. It goes to the rheostat so I can have more sensitivity. The power supply goes from 0 to 20 volt. The rheostat's going to make it such that a whole swing of the voltage knob here takes me through about 4 volts or so. I don't need to measure the voltage of anything anymore, but I'm leaving the ammeter here in the circuit because the diodes shouldn't have more than 20 milliamps going through them. I want to make them as bright as possible for the measurement, but I don't want to fry them. So if I keep the ammeter in, what I'm going to do is turn it up, the ammeter up to about I'm going to turn the ammeter up to about 15 or so milliamps. That's good enough. And you see the diode glows really bright, and I can move this wire down and illuminate any of the diodes that I want to. And now I've got too much voltage. I'm going to turn this back down to 15 or so. Okay, so that's basically how we get the diodes to light. I put both the diode and the spectrometer, which we'll talk about next, on lab jacks to help me with the vertical alignment of the spectrometer entry with the light source. This is the spectrometer. It's kind of got to get it far away so you can see it. Maybe I can zoom out. Is there a zoom? That's about as far as I can zoom out. So just quickly, at this end that we put closer to the light, there's a slit here. It's called a collimator, and its width is controlled by this knob. There's a focusing knob back here. This is called the objective because it's the part of the telescope that's close to the object we're interested in. In the middle here, we have the grating. The grading has 600 lines per millimeter. Let me see if I can show you that that's labeled. Sorry, let me see if I can get that in the focus. By the way, you can see the nice focus. Sorry, while I'm focusing it, you can see the rainbow effect of the prism. So 600 lines per millimeter. So the D in n lambda d sine theta is 1/600 millimeters. The way we measure angle is there is a vernier scale here, and the way this vernier scale is really hard to read, and I'll talk about that in a minute, but there's a scale that goes from 0 to 360 degrees in half-degree steps. That's an outer scale. And then there's an inner short vernier scale that goes from 0 to 30 minutes. 30 minutes is half a degree, 60 minutes is a degree. So you measure to the nearest half a degree, and then you count, then you measure minutes. Remember, a minute is a 60th of a degree. So we get a minute's degree angle reading. And then here is the eyepiece, and the eyepiece has a crosshair inside that I don't think I can show you, but if you look into there and there's light, you can see a fine crosshair. And it has a focus knob as well. And then this is a clever contraption down below here. There's actually two of these. If I loosen, where is it? If I loosen this knob, I can swing this guy around easily. If I tighten this knob down here, this guy is fixed, but then turning this knob adjusts it, moves it slowly, very slowly. So I can do fine adjust, coarse and fine adjust. So that's basically the idea. The vernier scale is hard to read, so there's two other things we need. We need, this is a magnifying glass, and so we can actually hold that magnifying glass, and I don't know if I can make this make any sense to you, but you can actually read much better through the eyepiece, through the magnifying glass. This magnifying glass comes with the spectrometer, and I also have a flashlight that helps a lot in illuminating. So you illuminate that and you make the reading. So that's about it. What's left is you align the diode with the collimator. This is harder than you think. Getting things aligned is really the hard part of doing the spectrometer. We can move things side to side. We can move things back. Generally what we do is move the eyepiece out of the way and just look straight through the objective, down the pipe there, through the spectrometer, and we can see the light that comes straight through. And then we put the eyepiece there and we measure the straight through light, the angle, and turns out these spectrometers they can be calibrated, and someone has actually calibrated this very carefully, and so the straight through light is really at 0 degrees and 0 minutes, which is very convenient and very nice. And so then we look around here, we swing around to find the first order spectrum of the diode light. It's off at some angle over here, and we put the eyepiece in front of us. We carefully align it, and then we come back over here and we measure what the angle is. And so that's what I did. And the data, it's kind of hard to see, but it's on this piece of paper. It basically is, the center angle is 0 degrees. And then there's an angle that I measured for each of the diode. Now, the diode, what I saw when I looked through that eyepiece is blurry and fuzzy and fat and wide. And so what I did is I tried to put the crosshair right in the middle of it. And I don't know how good it's going to come out, but that's what I ended up doing, and collected the data. And so just like before, I'm going to post this video, and I will scan and post the data as well. And make sure in your lab one sheet is reserved for calculating these wavelengths, and do as much uncertainty analysis as you can. And if it gets hard or impossible, then don't. I think that's all. I hope you're all well, stay safe, stay healthy, stay apart, and stay zen. Till next time, ta-ta.